This is the example we did last Thursday. Thank you very much. Lovely. Like I said last Thursday, we generally split all of the subspace in two large categories: orthogonal complement subspaces, span subspaces. For these two subspaces, when you go after bases in one of those subspaces, there are two methods. They are slightly different. Excuse me, guys. We're still discussing subspaces. Two methods. They are slightly different. For the span subspace, that's the method which you need to use. That's the method from last Thursday. For orthogonal complement subspace, in fact, if you follow the uploads, I have put the links already on Moodle, but given that we're a little bit ahead of time and we have free time, I decided to discuss it in class also. So here's the example, here's the demonstration of the method, how you find bases in the first category of subspaces, orthogonal complement subspaces. Another thing before I do, let me just open that first. Yeah, it's the example. It's a simple example, and again, computation-wise, it's the same old-fashioned row echelon form method. In fact, this example is so simple you don't have to do much of this row echelon form method, but in principle, it is row echelon form method. Before I do the example, I just want to announce, because one of you just came to me and asked what's going to happen in the test if you need to argue that something is a subspace or not. It may happen that in the test, which is this week, you may see a question which asks you to prove that something is a subspace. This something may be of one of these two categories, either span subspace or orthogonal complement subspace. In a test, you're not yet allowed to just make a reference. Once in a lifetime, we need to see your ability to argue that something is a subspace through subspace theorem. So in this coming test, if you see an orthogonal complement subspace, you cannot simply say, we proved in lectures that orthogonal complement subspace is a subspace, and this one is a particular example of the orthogonal complement subspace because you choose the vector A like so, and that will be the case, and that's why it is a subspace. In the coming test, it's something you yet not allowed to do. You need to argue that something is a subspace through the subspace theorem. Later on, you will do that. But for this coming test, if you see a question where you need to argue that something is a subspace, you need to use subspace theorem. Keep this in mind. So in this question, here's my orthogonal complement subspace. I'm not sure if this is from any tutorial questions, probably not. So remember, orthogonal complement subspace is the one which is defined via a formula of this type. And this formula basically is a dot product of a fixed vector with this random vector x, with the components x1, x2, x3. That's what we used to call orthogonal complement subspace. We know it is a subspace. I showed you a general argument. So in a test, if you see something like this, rather than make a reference in this coming test, test number 1, you just try to repeat that argument I showed you, and you will be quite safe and successful. But in this question, we need to find a basis for this subspace. And I'll show you the method. It's a very simple method. All you need to do, you need to consider this and solve this as a system of linear equations. Given that you have four unknowns, even though you only see 3 x letters, it's 4 unknowns, it's 4-dimensional space, x1, x2, x3 is missing because third component here is 0. That's why x3 is missing, but it's still there, formally speaking. So you got 4 unknowns and 1 equation. If you follow the general procedure, how you solve such equations, you need to extract augmented matrix, which is a matrix of this simple structure. It looks like as if it's a vector, just you see I no longer put commas. That's why that's a distinction, that's a matrix. 1 row, 4 columns. It is already in the row echelon form, isn't it? This is a leading column, that's a pivot, and that's a leading column. All of the other columns, they are non-leading columns. First semester method tells us that we need to parameterize the unknowns associated with these non-leading columns. Here's my parameterization. For x4, I choose the letter t for the parameter. For x3, I choose the letter s. For x2, my next choice of letters is u. And now I can solve in terms of these parameters. I can solve for the only leading variable, 1. Here's my solution straight from here. All I need to do now, I need to write this up in a vector form. Left-hand side, my x vector with 4 components. And then the right-hand side will be a combination of these solutions in a vector form. Look at this. That's the joint vector next to the t parameter, right? Because t parameter, it has component 1 in the 4th slot. It's not present here, that's why it is 0. It is not present here, that's why it is 0 here. And it is present here with the coefficient 1, that's why it is 1 in the 1st slot. S parameter, that's the joint vector next to the S parameter. 0 for the 4th component, 1 for the 3rd component, 0 for the 2nd component, and 0 for the 1st component. No S presence recorded here. And that's the joint vector next to the U component. Again, I just collect all of the coefficients next to U from these 4 identities. Look what happened. If you now we just done this boring method from the 1st semester of solving a homogeneous system of equations with which is undetermined. That's a term which one of you told me once. Nice term, by the way. It's an undetermined system. That's why we have multiple solutions, and we just solve this in the vector form. But now we can give this new language interpretation of this result. Every solution to this equation, aka every element of this subspace W or this SR subspace, admits a representation of this type. Isn't it? We just proved this. If you use my new language here on the right hand side, what are we looking at? We're looking at the linear combination of 3 fixed vectors, isn't it? It's a linear combination. 1 vector, 2 vector, 3 vector, and some coefficients next to them. So basically every element from this subspace, which is the orthogonal complement subspace, the space of the 1st category, we just made this element look like a linear combination. And in fact, the opposite statement is also true. Any linear combination like this, with any choice of t, s, and u, will be a solution to this equation, and thus it will be element of my orthogonal complement subspace. So what I'm saying, in fact, is this. We just proved with you that my W subspace, which is the 1st category of subspaces, which is the orthogonal complement subspace, it is also the span subspace. So through this method from the 1st semester, we just saw that the 1st category of subspaces can be, with some effort, seen as a 2nd category of subspaces, as spans, rather than orthogonal complement subspace. It's an interesting idea, actually. I was trying to keep these 2 categories apart as long as I can. I split the methods, one method for one category, one method for the other category. But it turns out, with some effort, you can always convert a subspace of the 1st category into a subspace of a 2nd category. That's how you do it, right on this slide. So in fact, I kept these categories away from each other, but in fact they are very close to each other with some effort. All right, back to the basis question. Remember, we still need to find the basis. These 3 vectors, they actually give me the basis. Because on one hand, they are spanning, isn't it? If you remember the term of what it means when someone says spanning. This set is spanning because it spans every element in this orthogonal complement subspace. And on the other hand, they are linearly independent. How do we see that? If you remember the methods, how to see that something is linearly independent in a span subspace. And we can treat this object now as a span subspace, even though originally we introduced it as a orthogonal complement subspace. To test that something is linearly independent, we need to collect the spanning vectors into a matrix and see if this matrix has all leading columns. For these 3, I didn't do it like in writing. I didn't collect this into a matrix on my slide. But if you do this mental effort, if you put these 3 into a matrix as columns. In fact, this should be the first column, this is the second one, this is the third. This will be already in a row echelon form, because that will be one pivot, this will be another pivot, this will be the third pivot. So all of these three will be leading columns if you do that. That's why they not only they are spanning, they also linearly independent. And that's why these three make a basis for my W, which now has dual category. It is orthogonal complement and span at the same time. And that's how you do it. So underneath it, it's the same method from the first semester, row echelon form and an analysis of the metrics which appear when you do row echelon form reduction. You need to learn the skills how to give this new language to the same events which happening when you do row echelon form as in the first semester. Any questions? Okay. The next thing which I'd like to discuss with you is there are a few questions in the yellow book which are like of a general nature when you have to argue linear dependence, linear independence, spanning, basis, and things like this. In order to help you with those, I already introduced some results. Like, for instance, we discussed with you last week comparison theorem. We discussed with you this result. Yeah, if you remember the slide from last week, span comparison theorem. It tells you some relations between the spans of two sets, given that these sets are either linearly dependent or linearly independent. It's one of the core results which you need to remember all the time when you do all this general argument with linear dependence and linear independence. The slide which I'd like to discuss today is the one which shows you one of the interesting ideas how you can use that. So from this slide, what we will need in my next slide, what we will need is, let me just see. We will need this result. So it's the very first one actually, the one which I call span comparison theorem. Let's just look for this again. It says this: if you have two sets of vectors of different size in general, M for Mary and N for Nicholas, and one of them is linearly independent. One of them is linearly independent. That's right. And the other one is spanning. See? S spans the whole V, so S deserves the name of spanning, whereas B is just said linearly independent. So linearly independent is smaller than the spanning one. That's the main idea of the whole comparison theorem. So the linearly independent set in size never exceeds any other spanning set in size. That's the main idea of the comparison theorem, and that's the idea which I would like to show you how to use this idea. I mean, there are different ways you can use it, but one of the ways, it's just to give you something when you do other questions with the yellow book. So my slide, which will use that, or which I will use to show you that, I call the second comparison theorem. Yeah. So look what it says. We are in a general setting of a vector space. Remember, when I normally write such a quadruple, it just means that we're just trying to argue in the very generality, we're trying to come up with the argument which fits any possible example of a vector space, and we have 6 or 5 fundamental examples of vector spaces. So this is a vector space, and suppose we have a dimension of this space is n. Remember, dimension is it's a size of a basis. The other if in this lemma says this: if we have an element, we have n linearly independent vectors, then this linearly independent will be spanning all the time. Okay, so once again, the first comparison theorem, the one I just showed you on the slide before, tells you that a linearly independent set never exceeds in size spanning set. That's right. This one, on the other hand, tells you that if you have a linearly independent which is as big as the dimension, it will be spanning at the same time. Yeah. and hence we can call it basis. Hence I can call it basis because basis, by definition, it's a set which is spanning and linearly independent at the same time. Look at the proof. It's a simple proof, just a few lines, and it's not really hard proof, but ability to come up with something like this, it's something we try to build in you. In yellow book, you will see a few other questions where we try to build this skill. Let's look at this. So my objective is to see that my set, which is assumed to be linearly independent, it's one assumption about this set, and which is in size is the same as the dimension. It's a second assumption about my set. My objective is to show that the set is spanning. So I need to convince you that any element I choose from my original vector space, any element I choose, it will be representable as a linear combination of these n vectors. That's my objective. Okay? I'll start like this. We know that the dimension is n. We know that the dimension is n. That means if I build a new set of vectors, look what kind of set I just built. I use my original n, and I just introduced into the set one extra vector, n plus 1, and n plus first vector. This x I randomly chose from my v. Okay? Because dimension is n, I insist that this new set I just built, it is linearly dependent. This is exactly the consequence of the comparison theorem I just showed you. Because if you assume otherwise, if you assume for a second that this newly built set is linearly independent, by the comparison theorem we just discussed, linearly independent set never exceeds in size a spanning one. Given that the dimension is n, this vector space has a spanning set of size n. So if you're assuming that this is linearly independent, you see a contradiction. You found a linearly independent set which in size exceeds the one which is spanning. That's a contradiction. That's why making an assumption that this is linearly independent, it's a wrong assumption. So this implication, it's a comparison theorem from the slide I showed you a few moments ago. Now after I made this observation, I'm going to exploit this, and it's a beautiful way to exploit this. When I first time saw it, I loved it, and maybe one of you will be will be able to use this idea in some other questions in the yellow book. If you will, that will be a sign that you've really mastered this concept. Anyway, so linearly dependent it is. We know it now. What it means to be linearly dependent. If I just use the definition of what that means, that says this. There must be scalars, n plus 1 of them, from my original scalar field f. There must be scalars, n plus 1 of them, with two properties. Not everyone within the scalars is 0. Not everyone between these n plus 1 scalars is 0. And on the other hand, the linear combination of my set of n plus 1 vectors with these n plus 1 scalars delivers 0. That's just definition of being linearly dependent. I'm still exploiting this definition. Let's listen to this now. I'm going to focus my attention on this lambda, the one on the coefficient which is next to my x, on my introduced vector, on my randomly chose vector x. I'm going to focus my attention on this vector. I'm going to investigate two possibilities for this coefficient. There are two possibilities for this coefficient. It's either 0 or it's either non-zero. Obviously, there's two mutually excluding possibilities. There's only a third possibility which enters this picture, isn't it? Logically, these are two mutually excluding possibilities. I'm going to study these two possibilities. Let's just focus first on this possibility, that lambda is 0. If lambda is 0, then this term basically vanishes, isn't it? If lambda is 0, this term vanishes. So the whole expression which you're looking at right now becomes a shorter expression, becomes an expression like this. And in relation to the shorter equation, this claim still stands, right? I mean, originally we knew that between my n plus 1 vectors, not everyone is 0. We made an extra assumption that lambda is 0, so the rest of the coefficients, the rest of n coefficients, one of them must still be non-zero, otherwise this claim is not true. But this is a contradiction, isn't it? Because if you have something like this equals 0 and not every coefficient is 0, it means it is linearly dependent. And that contradicts to the original assumption that the set S is linearly independent. So this possibility we started, we finished studying this, but it's impossibility. It cannot possibly happen. So is my fixing of that. Not everyone in the remaining coefficient is 0. And that is a contradiction. That contradicts to the assumption that the set S originally was linearly independent. So the only option for my lambda is this option. So let's just study this possibility for my lambda. What does it say? If this coefficient is non-zero, then I can solve. That's the idea actually we saw once. I can solve for this x now because I can divide by lambda. If I'm sure that lambda is non-zero, I can divide by it. So if I solve, that's what I'm gonna get. And this is exactly what I'm heading to, right? I'm heading to, so I can claim now that x belongs to the span of x1, x2, and xn. And so S is spanning. And that's the end of the proof, actually. It's as short as this. My objective was to choose a random vector from V and convince that this vector will be in span of S. I just did it. For my randomly chosen vector, I showed that this vector will be representable as a linear combination of my x1, x2, xn's. And that's the argument which does so. Like I said, if anyone in this class will ever be able to do something like this on your own, you will make me proud. My skeptical and sarcastic side tells me that probably it's never going to happen. But maybe some of you will surprise me. Who knows? It's a very high level of argument with the linear dependence and linear independence. If you're able to come up with something like this, it means that you reach that level. Normally, students in this class, they are not at that stage of mathematical evolution yet. But who knows? Any questions? It never hurts to try, isn't it? Okay, so strictly speaking, we're almost over with the discussions of vector spaces. We're going to take it now to the next level, linear maps and stuff like this. But before we do that, we do it next week. I mean, we still have time today to discuss some extra topics in relation to the vector spaces alone. And this is the extra topic, which is called orthogonal and orthonormal systems. So I don't know how much you've done already, how much you practiced with the yellow book, with bases, finding coordinates of vectors with respect to the bases. But if you've done even a little bit of that, you probably know by now that this is, on one hand, it's a very powerful machinery because it allows you to express infinitely many vectors through just a finite set of vectors. That's the whole beauty of having a basis. On the other hand, computationally, it's quite intensive. Every time you need to find the representation of a vector with respect to a given set, you need to go through the row echelon form, you need to solve system of linear equations. It's computationally intensive task, trust me. Even for computers, in fact, it's computationally intensive task. Especially when you discuss like big matrices and things like this. In these circumstances, actually, there are special classes of sets for which this task becomes a lot easier. And this is these special classes. That's what I would like to discuss with you in the rest of today's meeting. these special classes of sets they call orthonormal systems. There aren't many of those systems. They are not easy to find, and they not look nice most of the time. Like it or not, that's the reality. However, when you have them, if you found one, dealing with such a system after you found one and after you have one becomes a lot easier than dealing with any other systems. That's why we treasure them so much, orthonormal systems, and that's why when we find them, we keep them handy. Okay, so you'll see this. I'll show you an example. You'll see how it works. So let's just first discuss what it is and why it is so valuable. I start with a system of n tuples. You see, n in here. Yeah, it's a system of n tuples. It has m elements. Apologies. Not necessarily the same as the size of the. Not necessarily the same as the dimension of your n-tuple space. We're going to call this orthonormal system if two conditions are met. First one is they are pairwise perpendicular, or algebraically speaking, if you take the dot product of any pair from this set, any distinct pair, it is 0, and B, if you take a dot product of the vector with itself, it's 1. If these two conditions are met, we call it orthonormal system. The first condition, in fact, it's the orthogonality, so the system is orthogonal. The second condition, it's the normal, so the lengths, if you admit such a term, because we're talking about n tuples, strictly speaking, there's no any lengths here, there's no any geometry or distances there, but if you just keep using loosely the same term as you used to use with the three-dimensional vectors, then the lengths are 1. Yeah. So this one you have to make sure this one is 0 for when indices are different. So they are pairwise orthogonal. You have to choose distinct pairs, and this is just when the length is 1. Sometimes, yeah, that's right. So, sometimes people replace B requirement with the weaker requirement, which I call B dash on my slide. If you replace the B requirement with the B dash requirement, so you require just the length to be non-zero rather than just 1, so it's a weaker requirement than this requirement. In that case, the system is called orthogonal system rather than orthonormal system. So you drop the part normal from the name because it's no longer normal. So look, what's so beautiful about the orthonormal system? I made a statement. I frame it as a lemma. Look what it says. If you have a vector which belongs to the span of this set B, that is, the vector admits the following representation. Any vector which admits representation like this, any vector from the span of this system, if you're facing a task of finding these coefficients, and you will be facing this task a few times in the yellow book, if you're facing such a task, in general, if you remember discussions from last week, you need to solve a system of linear equations. You need to take the row echelon matrix, augmented matrix of a system, you need to take this to the row echelon form, and all of these tedious computational tasks you need to perform in order to find these coefficients lambda 1, lambda 2, lambda m. However, if you're dealing with the orthonormal system, then you have a direct formula. You don't have to solve for anything. You don't have to take any matrices. You don't have to do any row echelon forms. All you need to do, you need to compute n dot products of your A vector with every element in your orthonormal system. And that's the main reason why people value orthonormal systems so much. For the orthonormal systems, you don't have to solve any systems of linear equations, and that's a huge advantage. And I don't know, probably in this class, nobody will ever reach the stages when you do like maybe you will actually. You from finance, right? So people do huge matrices there all the time. you will realize how much more efficient doing the orthonormal systems in comparison to general systems. I don't remember from the top of my head actually the orders of complexity. Well, it doesn't matter. Right, so why this is so? Not only the formula here is valuable, the method or the argument why this is so is also valuable, because you can actually read just this argument to some other settings, some other circumstances, and the benefit there as well, where you no longer have n-tuples, where you no longer have dot products. This similar trick will work there. That's why I'm going to show you. In fact, the yellow book has a few questions about like that, where you can't use this result directly, but you can use the ideas of the proof in order to make computations in those questions a lot shorter. So look what the proof says. It's a direct proof, in fact. There isn't much of the thinking. So what I will do is this. I'll take this. Well, there are m different identities here written, right? Your j index here takes m different values. So in fact, we're proving m different identities. I'll do it like I'll show you the idea on just one of them. So when j is 1, when this index j is 1, you see, I'll show you the idea on this one special case. The rest of the identities, the rest of the m take 1 identities, they are similar. So what I'm going to do is this. I'm going to take this right-hand side for j equal 1. I just did it right here in front of you. And I will replace this a. I will replace this a with my assumption. Remember, my assumption is that a came from a span. So my assumption is that a is represented as a linear combination of x1, x2, xm. So I will take this representation, and I'll sub it in here. That's the complete substitution. Look at this. Rather lengthy line, but that's all of it. And then I will start using the properties of a dot product. For instance, one of the properties of a dot product we know is distributive law, which means that I can take this factor and I can apply this factor individually to every term in the bracket. That's a distributive law. We can distribute this factor across the terms. So here's my application of a distributive law. I'm sorry. x1 dot product x1, x1 dot product x2, similar treat for the rest of the terms. The last one will be xm dot product x1. Just do it again. What's that? Quick. Now, when you look at these brackets, after I've done my distributive law, all of these can be approached through these assumptions. Every time you take a dot product with the x1 and your indices are identical, it's only once happens when the indices are identical, your result is 1. All of the other brackets, they are 0 because of the requirement a. And hence the result here, hence the lambda 1. All of the terms here, they will vanish except for the very first one, which will deliver lambda 1. And my identity is proved, isn't it? I took the right-hand side from here, and I concluded left-hand side. It's a very simple idea, very good to remember. Like I said, in the yellow book, there will be at least 2 questions where you can do similar tricks without dot products, but similar tricks in order to conclude something like this. Very simple idea, but we're done. Similar argument, absolutely similar. For instance, if you go second identity here, when j equal 2, that's my second identity. Again, if I use this representation for a, if I sub it in here, and I do distributive law, or simply speaking, if I expand my brackets, that's what I'm going to have. In these brackets, it only once happens when j equals j, right here, x2 dot product x2. all of the other instances, we will have different indices. 2 and 1, 2 and 3, 2 and 4, 2 and m. All of these instances, they are covered by the requirement A. All of these instances, they will vanish. And the result is lambda 2 as a second identity. So repeating the same steps for all of the other identities from this set of identities, the proof is finished. The proof is finished. Any questions? Okay. Right. I'll show you one example how this works in order to convince you once again that how effective orthonormal systems are. But before we do that, I'll show you one corollary on the same slide. And this is in fact question 52 from the yellow book. Look what it says. If you have a system which is orthonormal system, then such a system is always linearly independent. So in fact, there is no any linearly dependent orthonormal system. It's a very simple observation given what we just discovered. Given what we just discovered, it's an absolutely trivial, straightforward observation. Look at this. You start off as usual with a linear dependence on independence. You make an assumption. You make an assumption that you have discovered m coefficients which make a linear combination 0. In order to convince that this system is linearly independent, you need to show that all of the coefficients must be 0. Like I said, normally you need to solve a system to find these coefficients, but for the orthonormal system, here's the solution straight away. So if I treat this 0 as this A vector, I can discover each of these coefficients by using this identity and using 0 in place of this A vector. That's why I call it a corollary. That's why it is straightforward. So now I can immediately say that lambda 1 coefficient through this formula, it's a dot product of 0 and x1 vector. No matter what x1 is, 0 vector will always make it 0. Lambda 2 coefficient, for the same reasons, through this identity, it's a dot product of my 0, which plays the role of A vector, and x2 vector. It is 0 number again. And the rest works the same. The mth one, it's a dot product of a 0 vector with xm vector. That's a 0. And this is it. That's exactly the content of any argument which involves linear independence. I made the assumption that linear combination is 0, and I presented a justification which shows that the only possibility for coefficients is to be each of them individually, simultaneously, and independently 0. And that's the end of it. Any questions? Thoughts? All right, so I'll show you one example of an orthonormal system. You'll see why, this law in mathematics, it's a general law which says the law of conservation of difficulties. You cannot avoid that. On the one hand, orthonormal systems, they bring quite a simplicity when it comes to finding these coefficients in representations. It's quite a simplicity. On the other hand, because of the law of conservation of difficulties, there must be a catch somewhere. I'll show you the catch now. Beg your pardon? You see the catch already? Question 73 from the tutorial book is very typical. Here's the example of an orthonormal system. here's your catch. Systems themselves, orthonormal systems by themselves, they're not easy. I mean, they never look nice. I mean, most of the time they don't look nice. There are some exceptions, very limited number of them. They don't look nice. That's a typical example. There are always roots in there and things like this. So finding them, it's not an easy task. Not for you, for everyone, even for computers, for geniuses. It's not easy to find the orthonormal system. So when we have them, we treasure them. If you have them, the rest is very easy. But finding them, it's a separate, significant task, and you're lucky because you're not going to be facing this task and this topic, finding orthonormal systems. But using them, it's a piece of cake on the other hand. Well, this is an example. That's the orthonormal system. We can check this directly. So I claim that this system, S, which consists of these three vectors in R3, it is orthonormal. Here's a check. For instance, length of x1, length of a vector, it's the sum of the squares under the square root. If you square these two 1 on root 2's, add them up, it's 1, root is 1. Length of x2, similar story, 1 on 3 plus 1 on 3 plus 1 on 3 is 1. Length of x3, again, 1. So it is a normal system. Normal means unital vectors all the time. Dot products, we have three possible couplings, right? If I couple x1 and x2, that's a dot product. I insist it is 0. Yeah, it is actually. Second coupling, x1 and x3, 0 again. It's because we got like a plus and minus, plus and minus. And the third coupling, it's a longer one, x2 and x3, because no longer you can benefit from 0 here. It's a longer coupling. 1 root 3, 1 root 6 with negative, 1 root 3, 1 root 6 with another negative. And these two, yeah, it's 2, so it is 0. So it is indeed an orthonormal system. So if I have another vector, say fourth vector A, which is a nice simple vector with integer components, negative 1, 3, 4, and if I'm facing the task of expressing this vector as a linear combination of these three, so if I'm facing the task of finding this presentation, this A vector in terms of x1, x2, and x3, so I'm facing the task of finding the unknowns, lambda 1, lambda 2, lambda 3. This time, I no longer need to solve any systems of linear equations. I will be dreading doing that if I need to, because the system, it will be a system with horrible coefficients, with roots and everything. But given that we're looking at orthonormal system, I don't need to do that. All I need to do, I need to compute three dot products. For lambda 1, that's the dot product I need to compute. x1 with this A vector. Given that the 0 in here is a computation. That's a lambda 1. Negative 2 root 2. For lambda 2, that's a similar computation because of the lemma we had before. Similar computation. And that's the coefficient. And lambda 3, again, it's a computation. It's a pure computation. That's the lambda 3. It's the dot product of my original A from above, this A, and this x3 right here. So I can say now that the coordinates of my A vector with respect to S, which is a basis, it must be a basis, isn't it? Because it's linearly independent system. It's a comparison theorem, by the way, the one which is proved today. Because we have three elements, dimension of dimension of R3 is 3. So any system which is linearly independent and which has as much element as a dimension, as many elements as a dimension, I'm sorry, it must be a basis as well. So this system is a basis, and that's a representation of my vector with respect to this basis. Any questions? Good. We only have 4 minutes left. Like I said, we basically finished our general discussion of vector spaces. We need to move on to linear maps. I'll show you in the remaining 4 minutes. I'll show you not a complete presentation, but just the beginning of it, just key ideas of this technique. I mean, the technique from the slide before, when we argued that when you find a representation of a vector with respect to an orthonormal system, all you need to find 3 dot products. Very similar ideas, they work in other circumstances where you don't have dot products. And I'll show you one of these examples. It's from the yellow book. I'll give you some key ideas. You'll finish it on your own. Oh, I have a recording from last year, I think, complete presentation from last year. I'll publish this and you can follow that if you won't be able to recover it on your own. If I remember correctly, this is the question 79. Yes. The question 79 from the yellow book. It just discusses this, what's called Pauli spin matrices. It's the term which is totally relevant to our discussions, but just to impress you, we introduced this term. It's the Pauli, it's a very famous physicist from early 20th century. He made quite a few significant contributions to the quantum mechanics. In particular, he introduced these matrices to describe some models of electron behavior. 4 matrices like this, with complex entries, by the way. 4 matrices like this with complex entries. What are you, scared of Pauli matrices? Good? Yeah, they're lovely actually. No, they have some lovely properties. We don't discuss physics here, of course, but the question goes to ask that these 4 matrices, if you combine them as a set, it will be a basis in this vector space, 2 times 2 matrices with complex entries. It will be. Yeah, it will be. In fact, the question just, if I remember correctly, question doesn't ask you, ask you to show that this is a basis, but it is not the only way to do it, but actually it's a beautiful way to do it, what I'm about to show you. What you can try to analyze with this question is this. You can introduce an instrument, a tool, which resembles dot product a lot. It's no longer vectors. I mean, it's no longer n tuples. It's matrices this time. They don't have any dot products. We don't know how to compute dot products of matrices. We don't have it. We simply don't have it. Yet, we have a special tool, which is just for matrices alone, which works very much like dot product. Look at this. I'll show you the tool, and the rest you can investigate on your own. Let me just take an arbitrary matrix, 2 times 2. Any components, A11, A12, A21, A22. For such a matrix, there is an object which is called trace, and it's just the sum of diagonal entries of your matrix. So when you sum these two, it will be a number. It's a number which is called a trace of a matrix. And that's how you normally write this. Trace A. It's like a determinant, for instance. It's another number which is attached to a matrix. Trace, it's another number which is attached to a matrix. Now, if you compute something like this, I'll fix a typo though, it was supposed to be asterisk here. If you compute something like this, and remember, sometimes I use the colon to emphasize equal by definition. That's a good place to use that technique. If you introduce a coupling of 2 matrices, A and B, which normally people write with these angle brackets, and that's how you introduce this coupling. You take 1/2 and then you take a trace of a product of two matrices A and B. If you introduce such a coupling, I claim that this coupling will behave as dot product behaves for n tuples. And when I say so, what I mean is this. What I mean is this. No, what is it? Yes, what I mean is this. If you compute this coupling for these Pauli matrices, it will be 1 when you take the same matrix with itself, and it will be 0 when you take this coupling for pair of distinct Pauli matrices. That's what I mean when I say it behaves as similarly to the dot product for n tuples. This single observation, that there is such a beautiful coupling for matrices, it will help you to repeat the argument which we done for n tuples. It will help you to see that if I looking for a presentation of any matrix A as a combination of my Pauli matrices, I don't have to solve anything. If I want to find these coefficients, lambda naught, lambda 1, lambda 2, lambda 3, all I need to do, I need to find these couplings of my A with each individual Pauli matrix. Yeah, well, the same for A naught, it's a quite expansion here. So, in this regard, the person who first discovered that there is such a beautiful coupling for matrices, which works as good as the dot product, he was a genius. We now follow his steps and see how this coupling helps us to do computations easier with matrices. It's not a complete slide. I just showed you some key ideas of that. With some effort now, I'm sure most of you will be able to recover the rest of it and finish the question 79 with this beautiful coupling, which is sometimes called inner product, similarly to dot product, inner product for matrices. But having this, the rest becomes most of the time routine. You just need to follow the same argument I showed for the dot product. If you won't be able to do that, I'll publish the complete video argument for this, and you can see that if you like it. Any questions? No? Thank you very much. We're done for today. Thank you.